everybody. My name is Jack, and today I'll be presenting my work named Spiffy, Enabling File System Aware Storage Applications. This is work done at the University of Toronto with my colleagues. So let's begin. So file system aware applications are those applications that work with file system metadata. Examples of such applications include our partition editor, a file system checker, and a defragmentation tool. These applications bypass the VFS layer and operate directly on file system metadata structures on disk. Therefore, writing file system aware applications require detailed understanding of the file system format, including the ability to identify and interpret file system structures. These applications are essential for the successful deployment of a file system, since, for example, people will likely use a file system only if it comes with a file system checker. However, there are several problems with writing and deploying such tools. Currently, these tools have to be developed from scratch for each file system. Moreover, these tools require significant file system understanding and are thus typically developed by file system experts. Even so, these tools have bugs, and these bugs can lead to system crashes, data corruption, and security vulnerability. For example, the NTFS progs library had a bug that was caused by misinterpreting the NTFS metadata. The size of the master file table, or MFT record, can be interpreted in two ways. It is the number of clusters per record if the value is positive. Otherwise, it is 2 to the power of the absolute value of the field if the value is negative. So, unsurprisingly, the NTFS progs library misinterpreted this field and corrupted file systems when resizing partitions. The root cause of all of these problems is that these tools are inherently hard to write because the file system format is complex and poorly documented. These applications require detailed knowledge for traversing and processing file system metadata. Since different file systems use different metadata structures, an application cannot be reused across file systems. In addition, these applications need to be robust to file system corruption, or else they can crash or cause even more corruption. Our goal for this work is to simplify development of file system aware applications in two ways. First, we would like to reduce the amount of file system specific code that application developers have to write. Second, we would like to make it easier to write applications that work for multiple file systems. We also want to improve the robustness of these applications. In particular, we would like to enable correct traversal of file system metadata and ensure type-safe access to file system metadata structures. Type-safe access helps with detecting corruption when reading metadata from disk and also before writing metadata out to disk. This, in turn, helps reduce error propagation and further corruption from spreading. Our approach is embodied in the Spiffy framework that helps developers with building file system aware applications. The main idea is to have file system developers specify the format of their file system. With this specification, we can generate the Spiffy parsing and serialization library. Application developers can then use the Spiffy library to build robust file system aware tools. Our approach to specifying the format of the file system is to have file system developers annotate the metadata structures in the headers of the existing source code. Next, we use the Spiffy compiler to process the annotated metadata structures to generate a library that provides a generic API for type-safe parsing and serialization, as well as facility for traversing the file system. Lastly, the application developers can use the Spiffy library to build robust tools. Since the Spiffy library is standardized for all annotated file systems, it is easier for developers to build applications that work for multiple file systems. To summarize the talk thus far, we've described the difficulty with writing robust and generic file system applications. Now, we will talk about the details of the Spiffy framework and how it helps with this problem. As a first step, we need a complete specification of the file system's format, which will enable type-safe parsing of file system structures. Ideally, we should be able to extract the format specification from the metadata structure definitions in existing source code. However, these structure definitions do not completely describe their actual format on disk. For example, the slide shows that the definition of struct foo in a file system header file. In it, there are two fields called size and bar block pointer, both of a little Indian integer type. By looking at the name, bar block pointer, a programmer may deduce that this field points to a block of type bar block, but there is no way to know for sure. So our solution here is to annotate this metadata structure so that we can unambiguously specify this missing information. Here, we add an fsstruct annotation to struct foo to indicate that it is an on-disk metadata structure. Then, we add a pointer annotation right above a data structure field, such as bar block pointer field shown here, to specify that the field holds an address to a location on physical storage. Here, this pointer annotation specifies that the value contained in the bar block pointer field is the address of a block whose type is bar block. Pointer annotations provide the ability to specify relationships between file system structures. Thus, they allow traversal of the file system. For example, in ext4, from the super block, we can reach the ext4 journal and the block group descriptor table. In the descriptor table, each block group descriptor holds pointers to their block bitmaps, inode bitmap, and inode table. Each inode structure in the inode table also points to data blocks and directory blocks, depending on whether it is a regular file or a directory. Inode structures can also hold pointers to indirect blocks to support large files and directories. The main challenge with file system pointers is that they can store different types of logical addresses, requiring different mappings to obtain the corresponding physical storage address. Our solution is to add an address space type to pointer annotations to specify how to map an address to its physical location. Examples of such address spaces include the block and file address spaces that I will describe next. In the block address space, an address is simply the block number in the file system. This is the most common address space. In the file address space, an address is an inode number that identifies a specific file. For example, the ext4 journal is stored on disk as a regular file, and a field in the superblock stores the inode number of the journal. We specify this field as a pointer to the ext4 journal in the file address space. This address space requires mapping the logical blocks of the journal file to their physical locations. Traversal of every file system begins with a superblock. Therefore, a special annotation named FSSUPER is used to distinguish the superblock from other file system metadata. File system superblocks are always located in fixed known byte offset on disk. Therefore, we specify this information using the location argument. Here, we show an example of the ext4 superblock, which is annotated with the FSSUPER annotation. The location argument specifies that the superblock is 1 kilobyte away from the beginning of the partition. As explained previously, the sjournal enum is a pointer in the file address space that points to the ext4 journal type. One of the challenges with annotating data structures is that a field may refer to different types of metadata in different contexts. For example, pointers in an inode structure can point to directory or data blocks, depending on the type of the inode. We support such context-sensitive types by specifying a when condition in pointer annotations. The field is a valid pointer of the specified type only if the expression in a when condition evaluates to true. In this example, there are 2 pointer annotations to the same iBlock array. The first annotation specifies that iBlock is an array of pointers to dir blocks only when the inode's mode field indicates a directory. The second annotation specifies that this same iBlock is an array of pointers to data blocks when the inode's mode field indicates a regular file. The location of some structures are implicit in the code and not part of the structure definition in header files. For example, the ext4 block group descriptor table is the next block following the superblock, but the ext4 superblock does not have a field that points to this descriptor table. However, we need such a pointer to traverse the file system. So our solution is to provide an implicit pointer annotation that takes 2 additional arguments, a name and an expression. The name argument creates a logical pointer field that can be accessed and dereferenced. The expression argument is a C expression that specifies how to calculate the field value, which is the pointer address. In this example, the pointer annotation creates a logical field called sBlockGroupDescriptor and evaluates the expression at runtime to assign this implicit pointer field a value of 2 or 1, depending on the block size of the file system. Now, this field name can be used to traverse the file system from the superblock to the block group descriptor table. Spiffy provides support for vector types through the vector annotation. A vector contains a sequence of elements of the same type. The size of the vector can be specified in 3 ways. 1, the number of elements in the vector. 2, a sentinel value. And 3, the total vector size. So in this example, we show a vector with a fixed number of elements. The inode block is a vector of elements of type ext4 inode. The number of elements in this vector depends on the block size of the file system, as well as the size of the inode structure, which is specified in a field in the superblock named sinodesize. When the elements are variable sized, however, we can specify the total size of the vector. So for example, the directory indirect pointer structure has a single field called indirect block number that points to a directory block. This directory block is a vector of elements of type ext4 dir entry. We don't show the ext4 dir entry here, but they're variable size structures. So we specify the total size of the dir block vector as block size. Spiffy also provides a check annotation that helps to check metadata structure constraints at runtime. In the top example, we specified that the block size must be at most 64 kilobytes, and the magic field of the superblock must be exactly the ext4 magic number. The bottom example shows a fragment of the generated parsing code for the ext4 superblock. This example shows how check annotations are implemented. These checks help detect metadata corruptions. The generated Spiffy library contains a C++ class for every annotated structures and its fields. This allows us to implement type-safe parsing and serialization. It also allows us to introspect each structure and its fields to get their types, size, name, and parents. So we now take a look at the annotation effort required to completely specify each file system. The line count column shows the number of lines of code that defines the on-disk data structure in each file system. The annotated column shows the annotations we have added to the original structure definitions. In all cases, the annotations are approximately 1/4 of the total line count. These numbers include the types of annotations that we have shown earlier, as well as 2 special cases. We need to declare some metadata structures that were not declared at all. Such example would be the ext4 indirect block, which the code assumes is an array of pointers. So we also made minor changes to some structure definitions for clarity. In particular, when a single type definition is used across multiple different types. So for example, the block pointer in ext4 inode is an array of 15 pointers. The first 12 are direct block pointers, while the last 3 are indirect pointers of different types. We now show an example of building a file system aware application, a free space display tool that plots a histogram of the sizes of free extents available in the file system image. For this application, we require knowledge of how file systems keep track of block allocation information. The manual approach requires first traversing the file system to access the block allocation information, and then process this information to obtain the free space extents. In contrast, the Spiffy library provides the necessary traversal code so that the developer only needs to focus on writing code that processes the block allocation metadata. Here, we show a manually written function that traverses the ext4 file system to find the bitmaps that contain block allocation information. As you can see, a lot of boilerplate code is needed to walk through the intermediate metadata structures. What we want is an easier way to get to the functions that processes the block bitmaps without needing to write all the code to traverse the file system. Also, to fit this function on the slide, we have shown it without any error checks. In practice, these checks are easy to accidentally omit. In that case, any error during the traversal or corruption in the file system could cause unexpected behavior in the program, including crashes or garbage output. Now, we show the same application written using the Spiffy library. On line 3, we retrieve the super block through the fetch_super function. If the super block is corrupted, the function will return null. Next, on line 7, invoking the process_by_type function allows processing all of the block bitmaps reachable from the super block through its annotated pointers. This avoids the need to write any traversal code manually, so the developer can focus on just the code that processes the block bitmaps. As you can see, there are 2 advantages to using the Spiffy library. First, it simplifies file system traversal by reducing the need to know format details. Second, the library parsing routines include automatically generated sanity checks to help detect corruptions. Now, we show the same Spiffy application for Btrfs. The main challenge is that the process_by_type function takes a different structure type argument, an extent item, and a processing function for an extent item. The programmer can thus focus on just processing the Btrfs block allocation information. So we have talked about the free space tool. Now I'm going to describe some other tools that we have developed using Spiffy. Spiffy applications are file system specific while operating at the block level. They can read or modify the file system image. On the first row of the table are offline applications which operate while the file system is not in use. In this case, these applications are written in user space. On the second row of the table are online applications that operate while the file system is mounted. In this case, the applications are written in the block layer of the kernel, and they allow traversing and interpreting file system specific metadata without requiring any changes to file system code. So the first application I'll introduce here is the file system dump tool, which helps debug file system implementations. Our Spiffy tool is a generic tool that works on all annotated file systems. It parses all the metadata in a file system image and exports the result in an XML format using a variant of the generic file system traversal code shown here. This code uses two mutually recursive functions. The first function processes a file system metadata block and traverses the pointers contained in the block. The other function retrieves and parses the pointed to block, and these blocks are then passed to the first function, which allows traversing the entire file system. The main function is the only file system specific code that needs to be written here. The rest of the code is completely generic. So, continuing with the dump tool, since some file system metadata may not be of interest, the dump tool also provides API to help filter out irrelevant or unimportant fields or structures. For example, the ext4 dump tool does not export unallocated INO structures to XML. This tool has 482 lines of generic code and about 30 to 60 lines of file system specific bootstrap code for each file system. The type-specific file system corruptor enables us to test the robustness of file systems and file system tools by helping to check that they are able to correctly handle file system corruptions. The Spiffy corruptor allows us to specify a field of a particular type in a metadata structure and corrupt it on disk. This tool also works on all of our annotated file systems. It has 455 lines of generic code and less than 30 lines of file system-specific bootstrap code for each file system. We ran a series of corruption experiments using this type-specific corruptor tool and discovered crash bugs in existing tools such as dump E2FS for ext4 and dump F2FS, while no bugs were found in our Spiffy dump tool for all of the 3 file systems we tested. Incidentally, none of these bugs that we found were triggered by 5,000 random corruption experiments, showing the usefulness of the type-specific corruptor. We have also built an in-place file system conversion tool that converts from a file system of one type to another, while minimizing copying of data blocks during the conversion process. Currently, the tool converts from ext4 file systems to F2FS file systems. The generic code in the application has 504 lines. We read the ext4 metadata into memory with 218 lines of code, and then generate corresponding F2FS metadata with 1,760 lines of code. Most of these lines are needed to initialize F2FS structures. So here, we evaluate our conversion tool against a copy-based converter. The copy converter copies file system contents to another disk, reformats the source disk, and then copies everything back. This graph shows the time to convert a file system with 16 gigabytes of data, while varying the number of files in the file system. So with fewer files in the file system, less metadata needs to be converted, which reduces the conversion time for our tool. The copy converter performance is dominated by the size of the file system data and doesn't vary much for different numbers of files. In this log graph, we can see that the copy converter is about 30 to 50 times slower than our Spiffy converter. So the next two applications that we will present are implemented inside the kernel, and they operate while the file system is running. Our file system aware caching application supports various file system specific caching policies. It is implemented in the block layer, but it requires no support or any changes to the file system. The caching application identifies and interprets blocks as they are read or written. It uses the Spiffy library to identify the types of blocks and for interpreting their content to extract file system specific information. Our caching application implements several caching policies. For example, it can preferentially cache file system metadata blocks. To do so, when a block is accessed, we use Spiffy to distinguish between file system metadata and data blocks using file system independent code. Similarly, our caching application allows preferentially caching small files or a specific user's file. To do so, we use Spiffy to determine the file to which the block belongs. From there, we can determine the size or the owner of the file. Our use of Spiffy allows us to implement our file system aware cache with very little file system specific code. We also implemented a runtime checker that detects bugs that would cause file system inconsistency on disk. Our checker, similar to the block layer cache, identifies and interprets blocks as they are read or written. When the file system is about to commit its changes through transactional mechanisms such as journaling or copy on write, the checker uses Spiffy to compare the old and new versions of modified blocks to generate all the logical metadata changes in a transaction. For example, to create a new file in ext4, a new inode is allocated inside an inode block. A bit is set in the inode bitmap block, and a new directory entry is added to one of the parent directory's directory entry blocks. With support from Spiffy, generating logical changes requires significantly less file system specific code. We wrote two versions of the runtime checker for ext4. Our manually written version requires 2,099 lines of code, whereas with Spiffy, the lines of code is reduced by half to just 1,059 lines of code. And we are exploring further improvement to Spiffy to reduce this number even more. Okay, so now I will do a short demo of, yes, okay, questions.
So how would you handle this layout changes? Have two different versions of the library?
Two different versions of the block.
Yeah, if suppose I change the metadata.
So do you mean that you are upgrading the file system?
No, so I make a new version, new release, and there's a change in the metadata layout.
Yeah, so then you will have to add annotations as the developer. You will have to add something new.
Okay. So
Yeah, add something to the annotations.
that is okay for a new installation of the file system. Suppose you need to, you have a live file system already with the earlier version and you are trying to upgrade it. So you have two different versions.
Mm-hmm.
The old one and the new one.
Okay. So, sorry, I'm not too sure I understand what the question is. Like, how do you understand the format difference
So
in like live situation?
Can you have two different versions of the library based on the metadata, the layout changes, and then write a tool to do the on-disk upgrade?
I don't think it's possible to do a live upgrade. And currently the library is statically linked. So that means if you upgrade your file system and then you need to upgrade, for example, the checker to understand the new format, then you would have to compile a new version of the kernel module, for example, with the new library in it. It's not possible to live hot switch the library currently.
So if the file system change, your tool needs to be updated to add the annotation part.
Yeah, so you need to update the annotation, rebuild the library, and then rebuild the application. But the application should be exactly the same. Yeah, so unless there's file system specific changes to the application, for example, in a free space tool, if you were to change how you represent free space for that file system, then obviously the free space tool for that file system is no longer going to work until you change that correspondingly. But if it's the same thing, then you only have to update whatever you need to update, and then the tool should compile using the new library, and it should just work.
Are you making this tool public?
We will get to that soon. Okay, so I will do the demo. Let's see if I can do it quickly enough. Is it over here? Okay. All right. So I have to look this way to understand what's happening. Okay, so right now I'm just showing you a demo of both the dump tool and the corruptor. Okay, so right now we're building a new ext3 file system on dev SDB1. Okay, that's on the right side of the screen. So now I'm going to mount SDB1. And then I'm going to go inside it so I can make a few files for you so you can see that these updates to the file system actually show up in the dump tool. So here I created a new file named hello and then created a new directory called world. Okay? So after I created one file and one directory, then I unmounted the disk. And now I'm going to use the ext3 dump tool to show you the dump output, so the XML output of all of the file system's metadata. Okay. So before that, I'm going to show you that the UUID of the file system is exactly what you expect. So on the right side, we see that we created a new ext3 file system with that particular UUID, and you can find the same UUID in the super block of the new file system in this dump output. And here, I'm showing you that you can find the directory entries corresponding to the hello regular file being created, as well as the world directory being created. So now I'm going to try to corrupt this file system. So I'm going to pause this video quickly to show you some of the parameters that you can set. So as a first step, you always have to specify the name of the field that you want to corrupt. So not the type, just the name of the field. And this is usually sufficient because in file systems, most field names are uniquely identified. You don't even need to specify the type of the structure. So in this case right here, I'm going to try to corrupt the inode field of a directory entry. Okay? So you see that there's a field named inode, and it belongs to a struct ext3 durant. And so right now, I'm going to change its value from 12 to 777 here. So I need a -s3 here because there are actually 3 directory entries that comes before this hello directory entry. So the dot directory entry, the dot, and the lost and found, which is all in the root directory entry. So I need to do a skip 3 here to get there. Okay, so we enter the command. So here it says that it's written, or it's corrupted the directory block. So now we're going to do the dump tool again and see the differences between the previous image output and what happens after a corruption. Okay, so as you can see here, so before the inode number is 12, and now the inode number becomes 777, which is now an inconsistent file system image. So if you were to mount this, it's not going to find the file because the inode number that the directory entry specifies is no longer correct. Okay, so now on the bottom left screen, I've done a secondary corruption, which actually corrupts the structural integrity of the file system. So if I were to change the rec length of a directory entry to a different value, then now the format of the directory block would be considered incorrect. Okay, so that's actually going to cause format corruption. So here we show you that our dump tool is able to detect format corruption to a directory block. So if you were trying to dump this output, now it's going to tell you that there's an error fetching pointer from fetching pointer type directory block, which basically means that there was an error trying to parse this block. Okay, so on the top right screen, now I'm going to try to do exactly the same thing for Btrfs. Okay, so first we dump the output of a fresh Btrfs image. Okay, now I'm going to use the Btrfs corruptor to corrupt a field name block group. Okay, so you can see that this block is at address really, really far away. I can't read that number. Okay, so then I generate the afterward XML output, do a diff, then you should be able to see that here the block group got changed for an inode item from 0 to 876, as shown here. So all of these really file system specific things that we do with the corruptor, whoops, I should have paused it right there. So this is the code that you have to write for each file system. And then the rest of the code is completely generic, as was said in the previous slides. So as you can see, really always just some initialization code, and then setting up the block setting up the block size, and then everything else is basically the same. So now I'm going to do a second demo of the free space tool for ext. Oh, where's my mouse? Okay, so here again we create a new ext4 file system, and then we run the free space tool on it. So as you can see, it returns you a histogram, and we check the correctness of this tool against an existing tool called e2 freezefrag. And as you can see, the values are identical and correct. Oh my God. All right, but just to make sure that it is correct, on the left side here, everything is represented in number of blocks, which is 4K. On the right side here, everything is represented in the actual byte size. So that's why there's a discrepancy. So 64 megabyte is exactly the same as 16,384 blocks. Okay, you can do the actual math on that. All right, so now we have a secondary disk that has the whole Linux image within it, including the source code. So now we see the differences trying to get the free space for this particular partition. Then we should be seeing a much more fragmented file system. As you can see here, this file system is a lot more fragmented. And again, we can double check that all of the output is correct. All right. And the code for the free space tool is in the slides. Okay, how do I come? Oh. The problem is can't find my mouse anymore.
The two screens are different sizes, so you have to go up probably and then left.
Yes, I realized. Okay. From current slide. All right, let's keep going then, but not much left. So in conclusion, we have presented the Spiffy framework. So we provide an annotation language for specifying file system format, which enables generating a library for traversing file system metadata. The Spiffy library simplifies development of file system aware applications by reducing the need to write file system specific code, and it enables code reuse across file systems. It also helps developers write robust applications by providing type-safe parsing and serialization of metadata, and helping to detect file system corruptions. So to find out more, we actually have a FAST 2018 paper, but I think this is already posted on the website, the SDC website. And I also have a GitHub repository, but it is actually not public yet. So I need to do some fixes. Essentially, we had some undergrad coming here and doing some extra work, and we want to make sure that everything is kosher before we release this code. So we should be expecting a release in a week or so, okay? So, but this would be the link to find our code, okay? So thank you very much for your time. I'll take any questions. Yes?
Does it support ZFS?
If you would annotate it for us, then yes. Right? Yeah, if there's no other questions, thank you very much for your time.